Now that we looked at the concept of Minkowski sum, we need to introduce one additional concept. Because the thing is that we would like to introduce a Minkowski sum to enlarge the obstacles to do the motion planning for a robot. But the problem here is that once you enlarge the obstacles, the complexity blows up, and it's no longer clear that if you look at the union of enlarged obstacles, it will have a total of n complexity. Maybe just everything goes wrong and you get a shape that has n squared complexity. To be able to handle things like that, we need to delve a bit deeper into this area of discrete geometry. We introduce this concept of pseudodisk, and this is going to come in very handy later on. So imagine that you have a collection of objects or shapes or subsets of the plane. We call this collection a collection of pseudodisks if every pair of these objects intersect at most twice. The reason behind this definition, or the motivation behind this definition, is that if you have circles, well, circles intersect either 0 times, or they're tangent, so they intersect once, or they intersect at most twice. You cannot have two circles that intersect 3 times. And if you have a set of objects that have the same property or a similar property, then we call them pseudodisks. And actually, if you recall, in the last week's exercise classes, we actually solved a problem that showed if you have a collection of disks, their total complexity is linear, using some interesting geometric transformation. Here we want to generalize it and prove it for a bunch of pseudodisks. Okay, so that is not a pseudodisk, that is a pseudodisk. And one consequence of being a pseudodisk is that if you look at the intersection of two things, let's say the region of blue that is inside red, the boundary is connected. So that's what we're going to use later on. Okay. Right now we only consider pseudodisks that are polygonal. So they're made from vertices and a straight line segments. Okay. So now this is what we want to prove. We want to prove that if you have a collection of convex polygonal pseudodisks with a total of n edges, then the union complexity is linear, or in particular at most 2 times n. Again, this kind of generalizes what we proved for circles. So how do we prove this? Well, the first step is to identify where the difficulty of the problem lies. Right? So when you look at the vertices along the union, some of these vertices are actually the original vertices of the input, so like these green ones. But some purple ones are made from the intersection of the edges. Since there are n edges inside this picture, it is possible that every pair of them intersect, so it could potentially be that we have n squared, or O of n squared, or omega of n squared purple vertices, or intersection points. We would like to show that that's not going to be the case. But either way, we could say that the green edges, they're at most n, so we can discard them. So in other words, the difficult part of the problem is to bound the number of purple intersection points. To do that, we're going to use a classical idea that is called a charging argument. To be able to follow this argument, we do the following. We look at one intersection point. Actually, don't look at the picture yet, because the picture could be a bit confusing. I'm just going to explain what this picture and what this writing over here means. Let's say you have an intersection point, right? So you have this point V, you have this intersection point Q, that is a result of the intersection point of two convex objects. And furthermore, we assume that Q is at the boundary, which means that one of these 4 regions is actually the outside region. So let's say this part is the outside region, okay? And let's say you have E1 from the first polygon and E2 from the second polygon, okay? And therefore it follows that this side of E1 should be inside polygon 1, and this side of E2 should be inside polygon 2, okay? Because we assume that that part of the picture is the outside world. Okay, so then look at this edge E. So this edge E1 penetrates inside the second object, and this edge E2 this way penetrates inside the first object. Follow edge E1. You have 2 cases. Either the edge E1 exits the first object or has a vertex inside. Similarly, for the second edge, you could either have a vertex inside or you could exit the object E1. We claim that it is not possible for both of these edges to exit the objects, their corresponding object. Why not? Well, for a simple fact that then that will create three intersections. Because these objects E1 and E2 already intersect once in Q1 at point Q. If E exits the boundary of the object number 2, there will be one intersection point at some point along this edge. And if E2 does the same, at some point there will be an intersection point along that edge as well. So therefore that's three intersections, which is not allowed because they're pseudodisks. So therefore at most one of them could have an intersection point inside. So let's say E1 has an intersection point inside, and that means that E2 needs to cut through the other object. So for example, this picture over here. It is of course possible that both of them have vertices inside. So let's say like this. Okay. But either way, it is clear that at least one of these edges should have a vertex inside. We charge this intersection point to that vertex. Okay. And then we would like to claim that every vertex will receive constant number of charges. If every vertex receives a constant number of charges, since there are linear number of, or there are n vertices, that means that there are at most O of n intersection points. Okay, so that's how the charging argument works. So the next step to finish off the proof is to show that every vertex can receive a finite or constant amount of charges. Okay. And to do that, we're just going to say that every vertex is charged at most twice, or particular, yeah. So, and actually we're going to charge it at most once, because in this argument we charge every vertex to itself, because we want to say that at most 2 times n. You get one charge from here, and you want to say you want to get one charge from here, so in total that's 2n. Okay, so that's if a vertex V is not in a pseudo disk, you get one charge, so that's easy. So let's look at a vertex that is inside the union. Okay, so let's say vertex V1. Well, how many charges this vertex could receive? Okay. So let's say it potentially receives a whole bunch of charges because of a bunch of intersection points. But then we're going to claim that only one of them, well, basically we're going to say that we reach a contradiction because these intersection points are inside, or they're not, but they will not be at the boundary. Okay, so essentially, let's look at the point that charges V, that has the farthest distance from V along this edge. Okay, so let's call that one Q. We're going to claim that any other intersection point of this blue polygon with any other object, that intersection point is completely inside. Why is that the case? Well, just this follows from the fact that we have assumed that the vertex V, and therefore this entire segment from V to Q, is inside this object. So therefore all of those intersection points will be inside. So therefore it follows that vertex V can receive one charge from there, so therefore we're essentially done. Well, okay, sorry, there is this other special case where V lies on the boundary, and then you can, this V is charged both for itself and also for an intersection. So therefore that's the only case you can receive 2 charges. So therefore we get that the total complexity of a union is O of n, or at most 2 times n.